Hello, my name is Altin Marai. I came from Polytechnic University of Tirana. This work is performed by using experimental data from a trial floating photovoltaic system located in a region having Mediterranean climate conditions. It is composed by 4 identical units having an installed capacity of 500 kilowatt peak per unit. The units are the world's biggest of their configuration, referred to the installed capacity and their diameter of 68.8 meters. Results include the energy yield, final yield, capacity factor, payback period, etc. They refer to an annual period for the year 2023 and offer a clear view regarding the floating photovoltaic system operation. The considered floating photovoltaic system will provide valuable information regarding the energy performance, the economic feasibility, and its operation under the Mediterranean climate conditions. It will be very important to notice any operational problem for the composing units of the plant regarding its stability, resilience, etc. The methods are based on the climate data, the energy yield, the final yield, the capacity factor, and the economic estimation. At figure 1 is shown one of the units. At figure 2 is shown the floating photovoltaic system, which consists from 4 units which are placed on the water reservoir of Banja hydropower plant. At figure 3 are shown the energy yield values, and at figure 4 are shown the final yield values. The maximum values of them are obtained in the month of August and the minimum values in the month of December. For the considered year 2023, it is noticed that the energy yield varied from 41 till 163.3 megawatt hour per month. The final yield varied from 20.5 till 147.5 kilowatt hour per kilowatt peak per month. The capacity factor varied from 2.8 till 19.8%. For the considered floating photovoltaic system, results a payback period of 9.6 years. Thank you very much.
Hello, my name is Beatrice Mina, and this poster deals with smoothed particle hydrodynamics modeling of wave energy converters within floating multipurpose energy platforms. This study presents the step required to model oscillating water column devices within a multipurpose floating platform. The platform to be simulated is the one portrayed in Figure 1 and was tested in the wave tank of Centrale Nantes, France. The peculiarity of oscillating water column devices, called also OWC, is their pneumatic power takeoff system. Indeed, water oscillates up and down in its chamber, compressing and decompressing the air pocket, which generates an airflow through an orifice, activating a turbine, converting wave energy into electricity. The objective is to model such a power takeoff within a meshless software called dual physics, starting from the simplest OWC configuration, that is a fixed one, and moving then to simulating a floating oscillating water column within a platform. The chosen method consists in employing a single-phase approach instead of modeling both the air and water phase to save computational time. In particular, the dual physics source code has been modified, adding an additional pressure term, PA, to the water particles momentum equation. This pressure depends on the variation of the water volume inside the chamber and is applied only to those particles belonging to the device chamber and at the same time to the free surface, as shown by the red particles in Figure 2. This method has been proven to work very well for a fixed oscillating water column and for a standalone floating oscillating water column device. In particular, considering a floating OWC with its motion restricted only to vertical translations, the simulated and experimental free surface elevations are in good agreement, as shown in Figure 3. Also, concerning a standalone OWC that is free to float, the algorithm works properly tracking the particles inside the moving chamber and adding air pressure only to them, as shown in Figure 4. The next step is the modeling of the whole platform, but this is not possible due to the high particle resolution required. Therefore, a solution can be imposing the platform motion to a standalone floating OWC as represented in Figure 5. Now, further modification of the dual physics source code is required to apply the pneumatic implementation to a device that is not free to move, that is not free to float, but is affected by an imposed motion. In conclusion, the novel pneumatic power takeoff implementation has been proven to work for many OWC configurations, both fixed and floating. These steps were necessary to deal with the simulation of an OWC embedded in a floating platform, which is still work in progress. Thank you.
Thank you very much for your interest in our poster. My name is Bonaventura and I am a postdoctoral researcher at Uppsala University in Sweden. This work is titled In Software Simulation of Floating Modular Energy Islands, the High-Fidelity Framework of Dual Physics. As you can see here, this work features a collaboration among several universities. And this is because it blends in the experience of people working on numerical modeling and on the design of renewable energy devices. For the simulation of wave energy converters and floating offshore wind turbines, it is essential to capture the high non-linearities that develop when ocean waves interact with the bodies of the devices we want to study. This is true for the devices I just mentioned, but it's also true for floating modular energy islands, and this is why we believe our work is important for the action moderner lands. Dual physics is the code we are promoting, is open source software, and is based on the smoothed particle hydrodynamics method, which is also known as the SPH method. The version of the code we are using has two libraries coupled in, and those two libraries are used for the simulation of catenary lines, or mooring lines in general, and of power takeoff systems. The results I'm going to show are based on a setup that was previously published by the authors of this work. Here you can see Figure 1, the configuration of a hybrid platforms, where a 5 megawatt wind turbine is hosted on a deep sea wind platform, but also you can see there are 3 wave energy converters attached to the same platform. Figure 2 proposes a validation for this configuration and compared against another numerical model, which is also for which the reference is provided. So the agreement is quite good, as we can see, and this will allow us to study the wave energy efficiency of the devices attached to the platform. So to conclude, we believe that such software can be used for the simulation of floating modular energy islands as well, and can produce comparable results and can help in the development of this concept for future applications. Thank you very much and see you around.
Hello everyone, my name is Fatih Karipoğlu. I am a PhD student in Izmir Institute of Technology, Turkey. Today I would like to mention about our mutual paper named as Conceptual Design for Modular Energy Island in Sustainable Energy Production in Crete. This presentation is the result of the work carried by others after the first training school of modernist cost action. First of all, I would like to give the general information about the Crete. Crete recently joined the Clean Energy for European Union Islands Initiative, which aims for islands to produce sustainable and low-cost energy. The project aims to help islands reduce costs and increase production using the renewable sources. To achieve these objectives, several sub-tasks had to be completed, such as firstly, the deploying of the energy island increased water based on the available wind, solar, wave, or renewable energy sources. And the second one is the determination of the current electricity demand and the current status. And the last one is the conceptual design of the floating structure, along with a selection of the technologies that allows to harvest the renewable energy sources. In the scope of this study, firstly, energy potential are investigated by using the energy potential atlas. When selecting a location for the energy island, social acceptance must be critically considered, as well as the impact on the already existing human activities in that area. For these regions, the island structure should be placed outside of the existing shipping routes, military region, and seafood production zones. According to these buffers, the best location for the proposed floating energy island is the eastern part of the Crete. For the design of modular energy platform, a hexagonal shape was defined for the modular platform inspired by the structure of a honeycomb. It has been proved by previous research that this shape is highly convenient in terms of modularity. Each hexagon will have the capacity to support up to 7 wind turbines, one on each nose plus in the center. In addition, 20% of the area in the floating platform could be used to to uh, allocate solar panels and a perimeter to provide the infrastructure for the energy converters. Finally, this modular platform is very important for the development of the energy islands. Thanks for your time and thanks for your listening.
The wind turbine technology is being improved constantly, and wind turbines and plants are bigger in both size and installed power. With much better wind power potential and vast space offshore, the further wind power deployment is expected offshore. Ambitious plans of some EU countries for intensive marine renewable energy deployment are imposing needs for energy hubs, which could act as point of common coupling. The transmission interconnection solution of the energy island implies either high voltage alternating current (HVAC) or high voltage direct current (HVDC) submarine cables installation. The HVAC technology could be the first choice for the shorter connection distances, since for longer distances it's limited by excessive cables' reactive power generation. From the other hand, the HVDC transmission solution requires offshore platform with power converters in any case, no matter of wind farm size and distance to shore. An energy island concept puts transmission system operators in the new operation challenges. Large amount of intermittent offshore production has to be transmitted to onshore grid, what could impact on the power system stability seriously. It might be that control of vast variable production and power transmission could be convenient with energy hub, controlling either directly from relative vicinity from energy islands or indirectly by controlling an energy hub itself. For stability's sake, the HVDC could be better solution since at each end of HVDC transmission line a power converter is necessary, enabling non-synchronized operation of the interconnection lines. Frequency stability issues would be minor in this case since each wind farm operates with its own frequency. Such a solution could increase investment costs, but some initial investment costs could be economically reasonable in long terms. As the summary, we can say that introducing the energy island concept imposes the new operational challenges to a TSO. Large amounts of marine energy are supposed to be collected by the energy island. Having such energy hub, a TSO could have more options to control dislocated marine energy sources. Thanks.
Hello, dear participants, for the cost action modular energy islands for the sustainable and resilience. For the workshop will be taking place in the Bochum in Germany at the time between the 2nd and 3rd September 2024. It's the PowerPoint presentation of our study. My name is Kemal Koca. I am participating of the Abdullah Gül University Mechanical Engineering Department and Renewable Energy Division with my undergraduate student named as Eyüp Bekçi. I will try to give the speech in at least 3 minutes, 3.5 minutes, and then I will discuss if it is possible. If we have time, we will discuss during the workshop duration. As the abstract, as you see here, there is a lot of discussion about offshore energy hubs. Sometimes people say that only as the energy islands, and how important they will be in process of the decarbonizing and the energy industry. By the leading of the way from the industry, the idea of establishing offshore energy island to capitalize on offshore wind potential in Northern Europe has gained many attraction in the national and European political discourse. From this motivation in this study, this research work provides an optimization analysis of different renewable energy resources on desired offshore energy islands on the surface of the offshore energy island to compensate, I mean, meet the demand, energy demand, and also to capture carbon dioxide of Western Black Sea offshore region of Turkey. For this study, the Homer Pro software program was employed to optimize the different renewable energy sources like wind and wave energies on desired OEI. Additionally, a comprehensive hydrogen production also will be evaluated in the study as well. For the objective of this study is to assess offshore renewable energy, offshore energy islands with various renewable energy sources for the Western Black Sea offshore region of Turkey to compensate energy demand. As you see here, we have the system configuration. We will use the wind energy and then hydraulic and then solar PV panels. At the essential target to meet this energy demand. At the rest of this electricity production, we will try to produce hydrogen production in this electricity. For the results part, as you see here, you know the Black Sea is the huge area, so which hotspot point is the so crucial for us? From the literature review, I mean the literature study, when you focused on this red region of the west part of the Black Sea, our hotspot will be pointed in the western region, especially near the Istanbul. At the figure 4, monthly average wind speed from the Homer simulation, especially from the January to March, and then the autumn season from the October to the December, we have really huge wind speed profile, resulting in the presence of the electricity production from the wind. As a conclusion, if I set the brief conclusion, 632 gigawatts of energy is produced annually, with the 17% of the energy generated from solar PV panel, solar energy, at 17.6 from the kinetic energy from water, the hydraulic energy, and then remaining the 65.4 from the kinetic energy of wind. As you see here, the huge portion of the energy production is coming from the wind because we have really in this region huge amount of the wind energy potential. The wind turbine utilized in this study is Enercon model in the capacity of the 4.2 megawatt, and then total is approximately the 40 turbines with a rotor diameter 115.7 meters are utilized on the energy island. So I really thank you very much for the listening to this video, and then whenever we arrive in Bochum, we will discuss in detail whenever you want. I thank you very much and see you there.
Good day to all. My name is Levent Bilgili, and I'm serving as an associate professor in Bandırma Oyundeğri University in Maritime Faculty. I'm holding a PhD degree in naval architecture and marine engineering. And today I will try to present my study titled Some Comments on Life Cycle Assessment of Floating Energy Islands. Energy island is a term that encompasses an innovative and important approach developed to produce a clean solution to energy supply. However, the construction and operation of energy islands can lead to the production of significant amounts of pollutants. Therefore, it is considered essential to assess the environmental impacts caused by these islands in a life cycle perspective. Life cycle assessment, or LCA in short, is an innovative and holistic approach to measure the cumulative environmental, economic, and social impacts of any kind of product system. LCA is considered a very useful tool to observe the impacts of different life cycle stages of a product, and thus it enables a comparison between sub-processes and provides data on which process should be focused for comprehensive improvement. Since LCA provides a comprehensive understanding on impacts of a product or product system, it is becoming more and more popular, and its area of use is expanding. Energy islands can be considered a very important and clean alternative for energy supply. On the other hand, it is also essential to measure in detail the environmental impacts that artificial islands would cause. Thus, it will be possible to understand how long it takes for the electricity generated from renewable energy sources on these islands to offset the impacts caused during the island construction process. This study aims to draw attention to the assessment of energy islands from a life cycle perspective, a topic that has not been studied much before. It is considered a very important necessity to evaluate the financial impacts of energy islands as well as their environmental impacts. Besides, assessing the impacts on the ecosystem is also considered essential. In this way, environmental impacts will be minimized and the pathway will be paved for the construction and operation of energy islands in a more environmentally friendly way.
Hello everyone, this is Majid Karimirad. I'm presenting design and analysis requirements of offshore floating energy islands. We are in climate emergency and urgency combating carbon and global warming. And to do that one, we need structures and units that they can provide clean energy, renewable energy sources. In particular in offshore, because there are vast energy resources available that can help us to provide these clean and sustainable energies from wind, wave, tidal, and solar. These can be done as you shown here. This is a floating energy island using offshore wind, tidal, wave, and solar. Thermal energy can be added to that, definitely from ocean resources. The idea is that these structures, they accommodate power generators that can convert energy from wind, solar, tidal, and wave at the same time and balance energy. Then the energy production can be exported as electrical power by power cables to shore, or can be converted to other energy sources such as hydrogen that can act as storage and can be shipped around the world. But as you can see here, a lot of considerations should be considered. The dynamics of this structure in particular are very important because they are subjected to simultaneous action of wind, wave, and current, and also they are quite elastic depending to their design. As particular, we want to have them simple, cheap, and light. That means that then they are more slender, subjected to nonlinear higher order actions by the environmental loading, and they have components such as mooring, anchoring, shared even between different platforms, and then power cables that they are exporting. And they are moving bodies that they are subjected to these meta-ocean loads, as I mentioned. From design, technology, production, storage, and shipping, we can see in this slide that there are a lot of considerations such as meta-ocean site considerations. There, it is very important to have a precise understanding of directionality of the wind, wave, current, and then joint probabilities. And this is important not just only for the dynamic response and structural integrity, but also for balancing the energy and then increasing the power production. This requires proper design and assessment, considering reliability, safety, and resilience. Cost, for sure, is very important. Commissioning, operation, and capital. Social acceptance, we have seen that in a lot of projects offshore, social acceptance was important in arranging the projects and then resulted in delays. So environmental impact should be studied also. And finally, the power production functionality of the structure. As I mentioned before, then the question is that the power can be converted to other types such as hydrogen, oxygen, or it can use as desalination units. Then the storage part and then export products such as hydrogen that can be transported by marine around the world, and this results in future cities that they can use hydrogen directly or ammonia or other types overseas.
Dear all, welcome to my presentation. My name is Maria Stella Daraki and I am PhD candidate in the School of Production Engineering and Management at the Technical University of Crete. The topic of my presentation is energy harvesting with euxetic microstructures, piezoelectrics and sand circuits. As a general aspect, the sand piezoelectric systems can be excellently used in energy harvesting. This work is an initial investigation of study this effect via sand piezoelectrics and euxetics. According to the literature, through the vibration of the host structure and the behavior of piezoelectrics as sensors and actuators can harvest energy. From the previous works, the euxetics as spacing layers can enhance the vibration control. The structure under study is an aluminum beam and one piezoceramic type PIC 151. The piezoelectric patch is connected with a RL resonance circuit. Two steel euxetic microstructures as spacing layers are tested. The first is a 4 cutout microstructure and the second is a 9-star shape. On the left side of figure number 1, we see the 4 cutout euxetic microstructure, and on the other side we see the parts of the total structure, the beam, the euxetic layer and the piezoelectric patch. In the figure number 2 on the left side we see the 9-star shape euxetic microstructure, and on the right side we see the total description. From this first investigation is compared three types of spacing layers, a classical steel layer and the two euxetic microstructures. It is shown that the 9-star shape microstructure gives higher value of coupling factor. In the figure number 3 is presented the voltage, the mechanical and electrical power which are produced from the vibration. On the left side is referred to the 4 cutout euxetic microstructure, and similarly it is given the same quantities for the 9-star shape euxetic microstructure. From this analysis is concluded that the 4 cutout microstructure can give better results among the other alternatives. Further investigations are expected about the output energy, the power, the shape of the both microstructures, piezo and sand circuit components. Thank you for your attention. Have a nice day.
Hello, I am Mariana, a PhD candidate at the University of Coimbra. I am conducting my research within the Renewable and Offshore Engineering cluster at ECS. In this video, I will share with you some highlights of our paper Assessment of Cyclic Deformation Behavior of Wire Art Additively Manufactured Carbon Steel.
My PhD research explores the potential of using WAM combined with optimization techniques in structures subjected to variable loading, which is common in the renewable and offshore engineering sector. Despite advances on the topic, critical questions still need answers, particularly concerning fatigue behavior. In response, we conducted an experimental campaign on low cycle fatigue of WAM carbon steel and developed predictive fatigue life relationships that can be used for component design. Central to our investigation was the impact of orientation and through thickness location on fatigue behavior. So, after the production of the walls, coupons were extracted horizontally and vertically across 3 thickness locations. The conclusions of our study can be summed up in 6 points. We found a critical threshold at 0.6% strain amplitude, delineating the transition of a mixed cyclic behavior, cyclic hardening above and cyclic softening below. The material displayed a non-massing behavior, likely due to changes in cell structure and dislocation arrangement. Orientation and through thickness location exhibited minor influence on low cycle fatigue behavior, though slightly superior results were obtained from horizontal coupons. The 3 different fatigue prediction models, Baskin-Coffin-Manson, Smith-Watson-Topper, and total strain energy density, align well with experimental observations, with no statistically significant difference. WAM carbon steel showed inferior low cycle fatigue performance compared to conventional steel. However, it demonstrated consistency with previous literature and exceeded the expected performance in the elastic regime. SEM analysis of fracture surfaces revealed crack initiation from surface and from internal defects, likely stemming from trapped gas bubbles during fabrication.
In essence, our research not only provides novel design tools for WAM components, but also highlights the promise of using WAM carbon steel in fatigue-loaded structural elements. Thank you so much for watching.
Hello, I'm Marin Ivankovic and thank you for an opportunity to present you with results of our research about aerodynamic characteristics of airfoils equipped with vortex generators and gurney flaps in dynamic stall conditions. Dynamic stall and dynamic stall vortex increase fatigue loads, which result in reduced lifetime and increased maintenance cost in typical wind turbine applications. These adverse effects of dynamic stall and dynamic stall vortex can be mitigated by increasing the maximum lift coefficient of airfoil and delaying dynamic stall to a larger angle of attack, and this can be achieved by vortex generators and gurney flaps. Gurney flaps and vortex generators were typically studied individually in the literature, but there are also some evidence that combined usage of both devices may further enhance flow over the airfoils. The main objective of present work is to investigate the effect of simultaneous applications of vortex generators and gurney flaps on airfoils subjected to dynamic angle of attack oscillations at high angles of attack. To achieve objectives of this research, wind tunnel experiments were performed on a constant chord wing that was equipped with 2 different sizes of vortex generators that were placed on 3 different locations on airfoil, and 3 different sizes of gurney flaps on trailing edge. Experiments were performed for 4 different reduced frequencies between 0 and 0.15 and for Reynolds number 180,000. Aerodynamic loads were determined by numerical integration of pressure distribution recorded on 32 chord-wise locations. Optimal performance of airfoil was achieved when 0.7% chord height gurney flap was combined with 1.1% of chord high vortex generators at 5% of chord from leading edge. While gurney flaps produced increase in CL max of 6%, without a significant increase in glide ratio. Vortex generators increased stall and reattachment angle of attack for up to 15% and reduced lift and moment oscillations by up to 68%, as visible on figure 2. In conclusion, it can be stated that this research provided another piece of evidence that simultaneous use of vortex generators and gurney flaps can further enhance airfoil performance in dynamic stall conditions. Thank you very much for attention.
Hi, my name is Marko Mančić. I'm an assistant professor from the Faculty of Mechanical Engineering of the University of Niš, Serbia. And I'm going to present to you a system that we have developed together with the Electrical Engineering and Information Technologies faculty from Skopje, North Macedonia. This is a mobile IoT-controlled photovoltaic dual-axis solar system. We have developed this as an innovative solution which relies on IoT technologies for control and operation for solar tracking instead of using expensive sensors such as solar radiation sensors, wind velocity sensors, and so on. And it can have 30% or more greater solar yield compared to fixed photovoltaic solution. The control is based on Raspberry Pi, Arduino Nano, and Arduino Mega hardware on a GPS sensor, but what is innovative of this, on this solution is its foldability and movability, and also it is possible for this solution for a user to basically turn it on, and the system will optimally orient itself towards the sun no matter in which position the user has put the system on. Here on this slide we can see the look of the system in the folded and unfolded position, and also we needed to embed some mechanical constraints of the system. The IoT solution is basically optimized as a plug-and-play solution for highest energy yield for a mobile solution. So the idea here was to include as much solar collectors as possible in the small surface area so it can be mobile. We believe that this system also can find its application in the offshore systems for small consumers, mostly on still waters, which may also benefit from the foldability of the system. However, for this, we of course need to work a lot more and develop this system further. The development of this prototype was funded by the Cross-Domain Technology Transfer Experiment as Smart for All grant agreement. Thank you for your attention.
Good morning. My name is Milana Rajic. I'm coming from University of Niš in Serbia, and I will present the paper Optimizing Offshore Floating Platforms with Digital Twin for Sustainable Energy Resource Assessment on Energy Islands. The main motivation lies in EU strategic alignment with the European Green Deal, which also states a commitment to address the also climate and environmental challenges through this transformative period. And it has the aim to transform approach that aims for sustainable, also inclusive, and also challenging society by 2050. And the main goal is to reduce the greenhouse gas emissions by a minimum of 40% that is compared to 1990s levels, and to increase the share of renewables energy sources at least at 32% by the year of 2030. And this Energy transition also highlights the immediate need to boost the installation rates of wind energy, particularly by quickly upgrading the capacity of existing onshore wind infrastructures. And also central to this, realizing these objectives in the application of digital twins and digital technologies, which also represents a shift to the design, but also in operation and maintains of wind energy systems. And this integration of digital twins allows for real-time interaction between the physical and virtual aspects of wind farm infrastructure that can significantly improve decision-making capabilities, but also operational efficiency and asset also reliability. And these developments not only contribute to the technical readiness of digital twins in the wind energy sector, but also to improve their social acceptance by providing reliable and low-risk energy solutions. Um, Despite the previous research and development effort that aim to expand the wind energy capabilities, there exists a gap in integrating advanced digital solutions, and it is particularly in the domain of digital twins. To optimize the design, operation, and maintenance of these offshore platforms. Previous approaches to scaling and improving the efficiency of wind farms of wind energy systems have primarily focused on the physical and engineering aspects of turbine and platform design. For instance, studies have explored aerodynamic optimizations, material science advancements for more durable turbines and site selection also methods in order to capture wind energy more effectively. And considering these efforts as important, they often overlook the potential of digital technologies to make some new approaches of new wind energy system to go forward. And these digital twins, which create a real-time digital replica of physical wind farm infrastructure, have started to gain attention, but not yet widely applied in the context of offshore floating platforms still. And this technology capability for real-time monitoring and also predictive maintenance as the second most important part, and also simulation aware and component health promise to reduce downtime and operational cost in a significant manner. And however, this review also indicates a gap in this also strategy that fully implements digital twins for the modular design and scalable expansion of offshore platforms to meet future energy demands effectively. And also to address the optimization and scalability challenges in this domain of the offshore floating platforms for wind energy, this paper conducts a review of the current state of the art, focusing on the three key areas. It is the application of Internet of Things, the second one, sensor technologies for data collection, also the application of artificial intelligence and machine also learning programs and algorithms for data analysis, and the use of fatigue analysis for simulation. And this literature review includes and analysis of existing scientific and also technical achievements to identify how they can be integrated into a digital twin framework for offshore wind energy system. And these recent significant innovations in this field, for example in Internet of Things and sensor technologies, are considered to real-time data collection on offshore platforms to be also included in this analysis. And for example, this prominent research that was included provided on how Internet of Things technologies can improve also the monitoring capabilities of renewable energy system and to highlight their potential to offer accurate and timely data for operational optimization. And these insights provide the solution to deploy this sensor across offshore platforms to capture data on wind speed, also turbine performance, and also to include also environmental conditions. And this review also covered the application of artificial intelligence and machine learning algorithms in analyzing the data collected from these sensors. And some of the research that was also analyzed demonstrated the effectiveness of machine learning in predictive maintenance for wind turbines as well, showing the potential to significantly reduce downtime and also maintenance costs. And in the field of maintenance and operations for offshore wind farms, the use of digital twins has been extended to analyze numerous aspects. And this also can be useful for and to create a virtual twins model that also mirror the real-time behavior of these wind farms, especially for real-time monitoring to predict some failures, and also life cycle management that can be also enabled and examined. And the pressing need for innovative solution to improve the efficiency and also scalability, but the also reliability of the model as well for the wind energy is addressed in this research in line with the EU Green Deal renewable energy targets that was previously mentioned. And this approach also include the new digital twin technology to integrate newly monitoring sensors that can be used in the future, and also the most advanced AI algorithms to create accurate digital replica of offshore floating platforms. And this, I can say, approach not only include the maintenance needs and boost asset, like I say, also reliability, but also support the modular design and scalability essential for adapting to future demands. And this presented solution progress toward problem resolution by using data acquisition from different sources, including sensor data, maintenance records, and also some conditions that can be weather changes or conditions in real time. And these data are processed and analyzed to inform the development of this virtual twin model. And the digital twin model not only like I said, support the identification of this critical component requiring maintenance, but also optimize the maintenance schedule based on the predictive analysis. And it can be useful really for this approach. And this method significantly reduces downtime and extends the operational life of the wind turbines. And this proposed solution contributes to the current state of the art by providing like I say, a framework for this systematic monitoring, but also risk management and maintenance optimization of offshore wind farms. And this approach not only improves the reliability of wind farm operations, but also ensures the safety of maintenance personnel that will be conducted the maintenance, and to minimize some potential environmental impact. And this discussion is supported by the outcomes of this review process. At the end, I want to thank you for your attention. If you have any questions, I'm on your disposal. You can contact me via email as well. Thank you.
Good morning. My name is Elena Ohai. I am researcher in the University of Aveiro of Portugal, and I would like to present you part of my work about the possible utilization of reduced graphene oxide for energy storage system. In our today life, energy is one of the more important subjects of human comfort. And all of us understand that the floating energy island, that is main topic of modern land construction, aims to harness the ocean's abundant energy in the form of wind, waves, and sun as renewable energy sources. However, the resulting energy must be stored. if it is not used immediately. So, energy storage system is very important to store and convert electricity and use it when needed, such as during peak hours. For this reason, different types of battery are studied. Graphene family materials are proposed to use as electrode materials in batteries and supercapacitors because of their high chemical stability and high electrical conductivity. In the presented work, graphene oxide as aerogel form material was prepared by freeze-drying technique. You can see it in figure 1, and heat treated to get highly porous and conductive material. Such materials was used for the preparation of composite electrodes. In addition, due to lithium is very expensive and rare materials, and as you know, lithium used in commercial battery, lithium battery for energy storage. We decide to use sodium ion electrolyte and study our graphene oxide aerogel-based electrode to test it. As you can see in figure 2 and figure 3, those electrodes were very stable chemically, mechanically, and almost no changed after high numbers of charge-discharge cycles. You can see that after more than 100 hours of continuous work, they are stable. So we think continue this work to modify reduced graphene oxide with another metal ions and study. Thank you very much for your attention.
Hello, my name is Tamara Bajc and I am Associate Professor at Faculty of Mechanical Engineering, University of Belgrade, and I am going to talk about the conceptual design of floating PV systems for large water bodies as a contribution to the energy production. These floating PV systems are widely used worldwide lately on different types of water bodies such as lakes, hydropower reservoirs, industrial ponds, quarries, and mine lakes, and of course offshore. They have a lot of benefits, for example, minimizing of occupation of useful agricultural land, protection from algal blooming, of course, decarbonization of electrical production sector, producing green electricity, and water evaporation decrease from large water bodies. This study analyzed the 6 largest lakes in the Republic of Serbia and its potential for electricity production using PVGIS software. For the purpose of the study, 6 locations are depicted. In Serbia, the average global solar radiation energy is about 1,400 kilowatt-hour per square meter. Also, conceptual design was done for floating PV systems concerning floats and PV modules, mooring system, lighting protection, combiner box, inverter and transformer, and connections to the grid. The results showed that for the Serbian largest lakes Vlasina, Đerdap and Zlatar, the energy output varies from about 1000 kilowatt-hour up to 1200 kilowatt-hours with fixed angle, and it can reach up to 1006 kilowatt-hours in case of tracking floating PV systems. The best location for floating PV systems concerning only electricity production potential is Vlasina Lake, but knowing its rare nature and variety of species, also other locations such as Đerdap Lake and Zlatar Lake are reasonable for consideration. Thank you for your attention, and for questions and more details, please contact me or download our published study. Thank you once again.
This poster is about impact of energy storage on the power system, applications and development directions. Energy storage is defined by the following criteria. Technical parameters: system power, amount of stored energy, full cycle efficiency, area occupied by the installation, energy density, operational period, method of connection to the electric energy system, level of reliability. Investment and operating costs, unit and total. Level of technology advancement. Impact on the environment. Possibility of possible expansion. On the poster you can see application of energy storage in power system. Development directions. By using more energy storage, the EU can reduce imports of energy and energy raw materials, improve the efficiency of the energy system and keep prices low by better integrating variable renewable energy sources. To meet this challenge, you must first analyze processes associated with various work cycles to enable predictive maintenance, increased reliability and improved design and manufacturing processes. Conduct system integration studies, focusing on how gas, electricity, heat and other infrastructure, e.g. electric car chargers, fuel stations, can be connected and complemented by gas, electricity, heat and/or fuel storage. Conduct demonstration activities, in particular how energy storage can provide energy services and monetize the added value of the energy system. Demonstrate the efficient use of energy storage devices. Analyze requirements for optimal integration. Figure 1 shows recent and ongoing large European community research projects financed by the Horizon 2020 program on the development of energy storage, divided into individual issues and technologies. This comparison shows that 23% of projects concern software. It is also clear that most of these technologies will find a place for small users who will need appropriate advice and service. Conclusions. Energy storage will play a key role in increasing the market share of zero and low emission sources, significantly increasing the flexibility of the network to fluctuations in power consumption on the recipient's side, eliminating the need for the producer to follow the recipient's consumption profile. The International Energy Agency estimates that limiting global warming to below 2 degrees Celsius will require increasing globally installed energy storage capacity from 140 gigawatts in 2014 to 450 gigawatts in 2050. Thank you for your attention.
Hello to everybody. My name is Yeşim Kamil Aktulu. I am from Dokuz University, İzmir, Turkey. The title of my paper or poster is How Great We Get an Inspiration Through the Architectural Design and the Structural Design of a 5M Wind Turbine by Repower in Moray Firth, UK. What I aim my aim is to examine the 5M wind turbine by Repower in Moray Firth, UK, to learn more about it, and by this way, I think that if we could examine the features of the former examples, we can get a better design for future. Now here, if we talk about the construction system 5M wind turbine, it has huge capacity to produce energy for powering around 4,500 houses. The design of the whole structure together with rotor blades, tower and foundation, and also the connection with seabed should be thought together to get the maximum advantage through the design of the wind turbine. In these built examples, the rotor has 3-bladed with a diameter of 126 meters, and the blades are constructed by glass carbon fiber hybrid. It is on the jacket substructure as its foundation, constructed with tubular structural steel elements. In fact, the discussion will be around how the foundation of the floating energy islands could be designed better through this jacket substructure foundation system of 5M wind turbine by Repower Moray Firth. As conclusion, for this example was the largest wind turbine in the world just before 2012, when the outcomes of this examination may be lightful, for the design of the one will be built in 2030. Thank you for listening to me. I think that by examining such kind of former built examples, we could go forward very fast. And this research could be done only by reading the published articles and by watching the videos about how it could be built. And I hope my paper, my poster paper will be a good inspiration for others. Thank you very much. Hello to University Izmir, Turkey. The title of my poster is What to be able to design a floating modular energy island. Here, I aim to underline the key points of how to design a floating modular energy island by getting the steps from the three former built examples, such as the Petronas platform, the Thunder Horse oil rig, and Troll A gas platform. When we try to discuss about construction steps of these three, we can say that Troll is one of the biggest gas fields in North Sea. And here, the Troll A has concrete legs, huge hollow concrete legs, 300-meter high reinforced concrete legs were built to carry the out as the platform with a multi-story living spaces for both accommodation and also working. And Troll A has a length sunk 36 meter into seabed, totally 472 meter. The slip forming construction method was used to construct the concrete legs, and the deck is structural steel, which has a dimension as 170 to 51 meters. The Petronas field project is in Gulf of Mexico. The Petronas platform has a length 610 meters over ocean base and 75 meters above the sea level, and it's a complete tower design, and this kind of structures may be tethered to the seabed by tension tethers and mooring lines. The Thunder Horse field is also in Gulf of Mexico. The Thunder Horse oil rig is one of the largest semi-submersible oil platform in the world, and its legs are enough to float, and this floating structure is tethered to the seabed using the long cables to keep the platform in the upright position in the water. And when we came to the conclusion, how many we will examine such kind of examples, we will get closer to the more perfect design for modular energy islands in future. Thank you for listening to me. This poster could be done by the researchers, done only by reading the published articles and watching the videos about how they could be built. Again, thank you very much for listening to me.